And now we're ready for the talk of Alexey Bufetov, Interacting Particle Systems and Random Walks and Hecke Algebras. Thank you for coming.
Yeah, thank you very much for invitation to speak here. I'm very glad to do this. So my talk will be about interacting particle systems and their relations to Hecke algebras. So it's it's very closely, I believe, related to the topic of the seminar, like solvable lattice models. So I will probably have them only like one slide near the end, but it's really I think it will be clear that this is very similar things. But I will start with probably the main object of my talk, which is asymmetric simple exclusion process, which is like short notation ASEP. So let me try to define it. So that's a model of particles which live on integer lattice, on Z, and they jump right to left according to certain stochastic rules. So the rules are as follows. So we have for every, so the simplest way to describe it, actually I will describe this in two ways, but like the simplest way to describe the rules are the following. So we attach to every particle two independent Poisson processes of rate 1 and rate q, which is less than 1. And then whenever like we have a point coming from Poisson process, particle tries to jump either to the right if this point come from Poisson process of rate 1, or to the left if it comes from another process of rate q. So there are like these intensities of jumps 1 and q, and 1 corresponds to jumps to the right and q to the left. And then there is exclusion rule. So if a particle tries to jump to already occupied position, then this jump doesn't happen. The configuration remains the same. And so the same if particle tries to jump to the left, and this position occupied, such a jump also doesn't change configuration. So all participating Poisson processes are independent. So these particles jumping independently, and then people study what happens with such a process so this is called this asymmetric because 1 greater than q. So there is a drift to the right. Particles tend to try to jump more to the right than to the left. Then a simple exclusion. Okay, simple just because particles jump only 1 step to the right or 1 step to the right to the left. Exclusion because there is like this exclusion rule, so there can be no two particles at the same position. And okay, asymmetric simple exclusion process ASEP. So like what happens with this process? So let me start with one specific question. So assume that I have the following initial configuration. So particles from 0 to the left, there are all positions from 0 to the left are occupied by particles, and all positions from 1 and to the right there are holes. So this is so-called step initial configuration. And so particles jump from left to the right. So there are like no convergence for like a stationary distribution on the whole integer, on all integer lattice. But like what's going on? So this type of questions, so like people were interested from like 70s, and like Harris, Liggett, and Ross. So these are like among peer pioneers of this field. So let me probably try to give a simulation, if I will manage to do this. So now you should probably see some simulation, which is due to Patrick Ferrari. So we can just look at the bottom. So there are like particles, blue particles on the bottom, and there are holes. And then when I click start, particle will jump from left to right. So I can do this again. So particles jump from left to right, and the question is like how we can describe this picture, and probably like to better explain what exactly I will be interested in this picture. So let us look at this picture from afar. So now particles are very small. You probably don't see individual particles. They are of very small radius. But okay, so then they jump. Yeah, so this is the first particle. It grows. Okay, let me stop it here. So we see a picture like this. So this is the first particle, the rightmost particle, and probably this one is the leftmost hole. And then, okay, some particles and holes are on this interval. So to the right of this position are only holes. To the left of this hole are only particles, and there is certain non-trivial region. And like what one can say about it it's actually visible from the simulation. Yeah, so actually what I will be interested is the density in this region, and it's visible from the simulation that the density here is, yeah, it's close to 1, so there are a lot of particles in this region, and it's close to 0 here, and then it somehow, yeah, more or less continuously changes from like right to left. Yeah, the density goes from 0 to 1. So that's a type of probabilistic result that I want to formulate. So I will need this later. So like what happens with this system? What happens with the density of this system? So I am returning to slides. I'm returning to slides. Yeah. So I hope you see slides now again. So the theorem, like somehow informally, tells that on this non-trivial region, the density goes linearly from 1 to 0. Yeah, so there is like this trivial half line with 0 density. There is trivial half line with 1 density. And in this non-trivial region, the density goes, the density is linear. So more formally, there is the following theorem, which is due to these papers in this context. So assume that we look at a certain position m, which is a function of time. Yeah, so time grows. So time is our growing parameter. We look at position basically y times t. Y is a certain real number, and then we multiply it by a large parameter t, and look at position m, which is basically y times t. Yeah, so m divided by t goes to 1 to y. And then the question is, what is the chance that this position m of t, we have a particle? And this is this notation, so eta of m of t. So this will be a notation that like a number of particles at position m at time t. So it can be either 1 particle or 0 particles. And then the statement is that, so this is a random variable, so a random variable which takes values 1 or 0. And the statement is that the probability that this random variable takes value 1 is given by this linear function from the previous slide. So here it's written, it's a formula for it written. So to the right of the rightmost particle, so it's clear that, okay, more or less clear that the rightmost particle, yeah, so it jumps one to the right and q to the left. So at time t, yeah, so its average velocity is 1 minus q. So at time t, it should travel 1 minus q times t. Yeah, so in the first order. So this rightmost non-trivial point is 1 minus q times t, and okay, divided by t is 1 minus q. So to the right of 1 minus q, we have density 0. Then the same can be said about the leftmost hole. So it travels to the left, and it will be at the point minus 1 minus q. So to the left of this point, it will be 1. So this is very logical. And then the non-trivial part is that in the middle, in this non-trivial interval, the density is given by a linear function. So here is the formula that connects this to point 1 and 0 by a linear function. So this is first part of this theorem. And the second part of this theorem is that if I look not only at one position m of t, but I will look, for example, at 2 neighboring positions m of t and m of t plus 1. So this like large integer lattice. I'm zoom in into some. First, I zoom in into position m of t, and then I also look at its neighbor, so m and m plus 1. Then we know by the first part that the Bernoulli random variable, so we have a particle with probability like this d of y, this density function. And the second part of the theorem is that somehow these random variables for 2 neighboring positions, m and m plus 1, they are independent. So they both have this distribution, and they are independent for neighboring positions. So m plus 1, m plus 2, m minus 1. So this is sort of like probabilistic introduction. So this is like probabilistic part that I will need, but yeah, the talk will become a bit more algebraic shortly. So if but I will need this so I will need somehow this from probabilistic part. So this theorem. So I wanted to start from with it. And then, the next thing that I want to introduce is somehow a generalization to multi-species system. So the system that we have here, it has only particles and holes. But one can also consider somehow more than two types of particles. So I can say that like particle and whole are like two different types of particles. And I think there were like talks in the seminar when there are like several different types of like several probably colors in vertex model. So this is, yeah, this is completely equivalent. But one can say one can say that we have like particles of different types. And actually I use all possible synonyms for these types, classes, colors, species. So it's all synonyms. So the only structure, so now particles will be of several possible types, and the only structure that I need on the set of these types is that there should be certain linear order. And then if I know like for every two particles, I can say which of these particles is more important and which of these is less important. I will introduce the following like updates of what I'm doing for two types of particles which stay in two neighboring positions. So I am doing the following thing. So if I have an update into two neighboring positions, I say that, okay, the more important particle jumps with probability 1 from left position to the right. And okay, so it must jump from left to right if they are in this order. And if a like more important particle stands on the right and less important on the left, then with probability q it goes to the left, and with probability 1 minus q it remains the same. So, and okay, just like for, so I would say that smaller type particles, they are more important, and larger type, so like the set of types will be will be indexed by real numbers, and like particles of smaller type will be more important than particles of larger type. And then yeah, I can do such an update with arbitrary set of types. So I just know, like I just need to know which of them is more important, which of them is less important, and then I run this updated to neighboring positions. And then with these definitions, through such updates which happen at two neighboring positions, I can rephrase my original slide. So here I attached Poisson processes to particles, but instead I can attach Poisson processes of rate 1 to pairs of neighboring positions. So for every pair of neighboring positions, so between every two positions, I have a Poisson process of rate 1, and which lives on positive reals. And whenever a point from this Poisson process comes, I try to, well, I'm doing this update according to the rules which are written here. And then if I have only particles and holes, then I will get exactly this process that we have seen a simulation about, and a certain like result about it. But like the advantage of this definition is that we also have in the same way we define the process for more than one and more than two types of particles. So one can have like 5 types of particles, and whenever we have a linear order on these types, we just do these updates according to these rules. And in principle, yeah, so these rules can also be thought of like, yeah, 5 vertex model, something like this. Yeah, so because of this 0, so it's so if it's like one can think about this update as a weight of a vertex. So if one wants to. So that's a definition of multispecies ASEP. And now again, let me say something like about probabilistic results about multispecies ASEP. So let me start with the following question. So assume that I have one second-class particle, like one like this middle type of particles, and the 0. Then I have particles on the left and holes on the right. And I start this ASEP, which jumps, like particles jump from left to right, like just as we have seen in the simulation. But now one of these particles is gray, and it can be, yeah, it can be somewhere. And let me ask what where is this particle? So let me denote its position as like S of t, and what one can say about the position of this particle, which is called second-class particle. So we have like somehow first-class particle, like real particles, then we have this one second-class particle, and then we have holes. So that's a terminology when we have only 3 types of various particles. So what one can say? Okay, a priori it's not very clear because, okay, so it's clear that this particle tries to jump to the right, yeah, because it pushes holes to the left. But on the other hand, whenever like this particles tries to jump over it, it is able to do this, yeah. So it can move to the right, and then the second class particle moves to the left. So second class particle can move either to the right or to the left. It's also somewhat clear that the situation is symmetric. It can go so it's like, yeah, so it's like this. If I call these holes and these particles, and then the system will jump right to the left, this will be exactly the same system. So it's somewhat clear that this position is distributed symmetrically with respect to 0. But other than this, it's not very clear, for example, whether it stays close to 0 or it's somehow spread out when time goes to infinity, like that this position of second class particle also somehow it can be in various positions far from 0. But it is known what is going on. So this is theorem of Ferrari and Kipnis, which says that actually like the second option is realized, holds, that this position is far from 0. So the distance from the position of second class particle at time t from 0 is of order t. So it's quite a lot. So if time is large, this s of t is also large. And it's also random. So so like in words, yeah, it can happen that the second class particle goes to the right. It also can happen that it goes to the left. So like formal statement is that s of t, so if I take this position and divide it by t, then this random variable converges to uniform distribution on this non-trivial interval. So we have seen that, okay, so there is an interval. So outside of this interval, this dynamic somehow doesn't change anything. Nothing jumped there. But inside this like large interval, the second class particle can be anywhere, and the distribution is uniform. So this is so this was proved in 95. Like one can also notice from like this formula, for example, yeah, so that the distribution function of uniform distribution on like this interval, it also includes this notation that I already had for before in this problem, which was for quite different systems. So this was only like no second class particles was here. So this was just a density for like this problem with particles and holes. And here, this density, okay, density of minus x appears in the distribution of second class particle. So one can think that this is just like, yeah, a coincidence, okay, so this is linear function, this is a linear function, all linear functions are the same. But we will see shortly that actually there is an algebraic reason for this, that these two quantities are actually equivalent to each other, so to say. So if we know this theorem about density here, it actually immediately gives the result about position of second class particle. So this is not how it was proved in this paper. So it was proved by like some other, like actually a short and beautiful argument about this position of second class particle. So algebra is not really needed for this result, but still it is somehow a first observation in like which will be important for us. So now let me ask the next question. So what will happen if I will just swap position 0 and -1? So I will place one second class particle at -1, then I will place a particle at 0, like a normal, like first class particle, and then there will be holes and particles to the left of -2. So compared to this is just like one swap, one change at position 0 and -1. And the same question, so what one can say about the distribution of the second class particle after large time t. And yeah, for example, when I first saw this problem, so I thought my intuition was, okay, so I knew already this, so this lives on a large scale, so it's of order time t, and then I just do one change, yeah, so it's just like change of one position. So in principle, it looks that it shouldn't be important, yeah, because it's just like change of one position, and then after time t, it should not affect, yeah, behavior of positions of which are of order t. But it turns out that it's not the case, and the following result holds that, okay, if I will study this position, like the position of this second class particle started from this initial configuration, then the distribution will not be uniform. Actually, it will remember. So just the fact that it started -1 and not at 0, and there was like this first class particle at 0, it will prevent somehow, it will try to lean more to the left rather than to the right. So there is exact formula. So this is some quadratic function as a distribution. So it's some parabola, which pushes this particle to the left of 0. So this is like a butterfly effect, right? So we change something just a little bit in the past, and it affects quite significantly the present. So it affects like this position. So this position is of order t. So it's large random variable, and it's much more leaned to the left. So this second class particle is more likely to go to the left. So this distribution still lives on this on the whole of this non-trivial interval, but now this distribution function, so it's more likely that it is to the left of 0. And again, and this is already like a result from 2 years ago. And again, so this is somehow once somehow certain algebraic structure is understood well, this is a very short like corollary of this probabilistic result. But that's already was a new result, like probabilistically, about like this initial configuration. So what I'm trying to do, I'm trying to somehow motivate certain like algebraic look on such systems, and also to explain that even like very simple algebraic facts lead to interesting and new probabilistic results. And also, okay, so some references need to be made. So actually, like this fact for q equals 0 is not new. So when particles just jump to the right, so there is no like, it's like complete asymmetry, not partial asymmetry, then it is known from a paper of Cator and Pimentel. And also like in paper of Alexey Bufetov and myself. So there was proof not only for this initial configuration, but there were certain like reasonable class of initial configurations and arbitrary q. So this was like a sort of like probabilistic motivation. Now let me try to explain this algebraic structure, which allows actually in a very short way to obtain this result from this somehow well-known for quite some time probabilistic result. So this is a structure of Hecke algebra. So let me recall what is this. So we have symmetric group Sn. So let us denote by like small s nearest neighbor transpositions, and by capital L of W, that this will be number of inversions in the permutation W. So then Hecke algebra, so this is an algebra. So first of all, this is a vector space. So in this case, this is a vector space of dimension n factorial, and its basis elements are labeled by permutations. So for every permutation, we have a vector t sub w, which corresponds somehow to this permutation w. And then we have a multiplication in this vector space, and it is known that this multiplication satisfies the following equations. So if we have a linear like a basis element corresponding to nearest neighbor transposition, so t sub s, so this s is necessarily nearest neighbor transposition, and we multiply it to arbitrary t sub w, where w is arbitrary permutation. So then there are two cases. So this like nearest neighbor transpositions, it's either add an inversion or removes an inversion from permutation w. And in these two cases, this multiplication works in a slightly different ways. So if it adds an inversion, so this L is a number of inversions, yeah. So if it adds an inversion, then Ts times Tw is just like T sub Sw. And if it removes an inversion, then we have 1 minus q times Tw plus q times T sub Sw. It might be once, okay, when I say this in this way, it might be already visible that this looks very, very similar to these update rules. So we also have like this q1 minus q coefficients, and we also have so these like two cases when it adds an inversion and removes an inversion. So this is actually tautologically the same, just two different languages. And okay, so this is known that object Hecke algebra, and like one particular simple operation on it that I will need is an following anti-homomorphism, which sends, so it's a linear map, which sends T sub W to T sub W inverse. So anti-homomorphism means that if I apply to, like if I have arbitrary elements from this Hecke algebra, H1, H2 up to HR, and I apply this involution I to its product, then it is equal to the product of involution applied to each individual elements, but just written in somehow in the opposite way. So yeah, so this is not a misprint. This is like a key property that here multiplication goes for H1, H2 up to HR, and here it goes in the reverse order. So this is actually a very important probabilistically. And again, yeah, it's a well-known operation and fact about Hecke algebra, the existence of such anti-homomorphism. Okay, so now how does this? How is this related to the previous like probabilistic considerations? So one can consider an object which it's reasonable to call a random walk on Hecke algebra. So let me formulate first this in somewhat generally. So assume that I have certain generators, so some set of elements from Hecke algebra, G1, G2 up to JK. And yeah, in order to somehow to do something similar to what I did before, so I will attach to each of these generators a Poisson independent process, or like independent exponential clock, which is just the same. And then, okay, so we want to define a certain sequence of random elements, continuous time process, which lives on Hecke algebra. And it works as follows. So whenever the clock, which corresponds to a certain generator GS rings, we multiply our current position to a new to this generator, and we get a new position, which is like GS times this current position. And okay, so maybe what one needs to have in what one can have in mind is that just example of like random walk in Z2. Yeah, so if like a person is in Manhattan, right? So if and like at every moment, like there is a choice of 4 possible directions. One can go a block in 4 possible directions. So like one can toss a coin twice, decide one of these 4 directions randomly, go 1 block, and then the next corner do the following procedure. Yeah, so this is a random walk on Z2. And then one can also think about this stochastic object also from like the point of view of group algebra, right? So if we have 4 generators which corresponds to go in like right, left, top, bottom, and then like random position at some point can be encoded by just like 1 element in group algebra of Z2, which is like a linear combination. Yeah, so like coefficients are probabilities that we are at certain point, and then multiplied by element of group algebra which corresponds to the group element corresponding to this point. And then like 1 step of this simple random walk in Z2 is the multiplication to the element 1 over 4 times the sum of elements corresponding to these 4 generators. Yeah, so like all theory about like random walk in Z2 can be, it's just like the study of powers of like 1 over 4 times the sum of generators to the power n. Then one studies this object. So that's more, that might be like a good picture to have in mind. And instead of somehow group algebra here, one considers Hecke algebra. Like and again, like what is like the key mechanism which connects probability and algebra is that if we have a random permutation, then we can encode this information about random permutation in 1 element of Hecke algebra. So if this permutation has a probability this random permutation, the probability that this random permutation is equal to W is this probability is kappa sub W, then 1 element of Hecke algebra which represents this random permutation is just like a linear combination. So for each W we consider an element of Hecke algebra T sub W which somehow encodes this element, and then we take coefficient kappa sub W which encodes probability, and then we take a linear combination. And then of course the point that the multiplication in Hecke algebra corresponds to our definition of asymmetric updates here. So these updates, which we're phrasing somehow probabilistic language, and this multiplication by nearest neighbor transpositions here. So then in this language, like in this in the setting, this becomes the same thing. And one can say that okay, returning to this like random walk on Hecke algebra. So we have generators, we have Poisson processes attached to them, and then we, whenever like clock rings, we multiply by generator our current position, and then we for like we have a like certain random element of Hecke algebra. Somehow this randomness comes from Poisson processes, and then there is another procedure. So from every element of Hecke algebra, we produce a random permutation according to this rule. So that's a bit somehow some generalities, but in like simple case, if I will take this generator as a element which corresponds to nearest neighbor transpositions, then this becomes exactly this multi-species ASEP which I defined. So it's just like two different languages. So here is even like some dictionary. So like if I have like this random multi-species configuration, it can be encoded as an element of Hecke algebra. Like this update with the rules, this becomes multiplication by T sub S. And like this ASEP evolution is element of symmetric group generated by a random walk on Hecke algebra with these generators. So, and then so there are also like some like projection to fewer types, which I will omit now. And also one obtains a certain like non-trivial probabilistic property from this involution, which swaps the roles of W and W inverse. Okay, so once written this like algebraic language, of course, one can try to generalize this like to in various directions algebraically. So one possible question: so what happens for other Coxeter groups? And at least in some examples, like for Weil groups and affine Weil groups, so this will be related also to some like ASEPs, which one can like it can like in BC case it will correspond to ASEP somehow, which lives on a half line and with a source. And for affine Weil group, this will correspond to ASEP on a ring somehow. But okay, we will not go into this direction. So how does this help probabilistically? Yeah. So okay. So I have said that this setting is helpful, but like how exactly? So let me say the key idea behind the proofs of, for example, this result. And first, let me probably say like why this, like how to get this result using this algebra, using this algebraic interpretation. And the key role is played by involution, by this involution. So how does this work? So let me say this in words for this problem. So here, one can imagine that instead of that we have just like 3 types, one can imagine that we have like infinitely many different types of particles. So at 0 stands the particle number, like with type 0, at -1 stands the particle of type -1, at -2 is particle of type -2, and so on. And then position, like what is written here, is a position of particle of type 0 at time t. And then when I will apply this involution, okay, when I apply this involution, so like position of particle of type 0 at time t, and when I apply this involution, the roles of permutation in its inverse will be swapped. And then I will be interested what type of particle stands at position 0. Somehow that's what will be given by algebra. And then like it will be visible somehow, like if one writes this just like on a paper, that will be visible that this is exactly what is given by this theorem, by this density. So it becomes, this involution somehow reduces the problem about second class particle here to this statement just immediately. Okay, I will not do this in detail, but yeah, this is, I think this is just like possible to do if one is interested in this. And then, like, how to solve this? So then, again, involution helps very much. But like, okay, so one uses the following idea. So if we somehow we start here in this problem with adjusted initial configuration. We started with a permutation which is not identical. We start, and generally we can try to study what happens if we start with some initial condition W. And then what one needs to study, so we like this initial condition is represented by this basis vector T sub W, and then we multiply it by a process, by a continuous time process, which comes from these Poisson processes applied to generators. And on the language of random walk and Hecke algebra, one wants to study such random element of Hecke algebra, so TW fixed, and then multiplied by this continuous time evolution W of T. And then the crucial idea, like that when we apply involution, we can study like these two terms swaps the order. This is something that completely not visible probabilistically, and also like which very easily comes algebraically. But this is somehow important that if I apply involution to these two terms, then I need to apply also involution to each of these terms individually, and then they will swap the order. So I will need first to study what happens with the evolution starting from initial configuration, and then in the end I will need to multiply by T sub W inverse, and then I also will need to have this involution in mind. And how like this strategy works on this specific example. So I first need to do, so this is something that's given by initial configuration, by identity permutation. This initial configuration is given by identity permutation. Then this one is not, but this one is obtained by just like one updated position minus 1, 0. And then if I do this here, so I do an updated positions minus 1, 0, and then start continuous time process. This is what I'm interested in. And if I will apply involution, I will need to do this in the reverse order. And eventually this will be again reduced to this situation. So all information will be contained in evolution, which starts from identity permutation. And then in the end, I will need to do this like one additional deterministic update. And this is very much analyzable from the second part of this theorem. So again, of course, I give just some ideas, and maybe it's not very, probably not everything is clear, but I'm concentrating on like the main idea, and like details I think they can be filled if this is really interesting. So like the point is that this involution allows to get from like one probabilistic results some quite different probabilistic results. It's no like real work after like this algebraic language is established. And then one can play this for, so in this like one example, this TW was just like one nearest neighbor transposition, but one can play this with larger permutations, and okay, also some results are available in this direction as well. So again, some references are needed. So yeah, in general, these connections between like multi-species ASEP and Hecke algebra, so of course it's present in various papers. And like the earliest that I have found is this one, Alcaraz-Rutenberg from 1903, and like some papers afterwards. But like somehow independently, but I think somehow this connection is somehow underused for like in probabilistic community. And like one indication of this is that like this class position symmetry, like this operation which corresponds to involution Hecke algebra, was also independently somehow noticed in some probabilistic papers. And like the main contribution there was that it was somehow non-trivially used for certain probabilistic results. And then it was like recently realized that indeed this just comes from this algebraic structure of Hecke algebra. And like I gave one example of such probabilistic applications, and there are like many more applications in these papers. So when I take as generators in Hecke algebra these nearest neighbor transpositions, I get ASEP. But like in the rest of the talk, I will try to discuss what happens if instead of these simple generators, one takes some other generators of Hecke algebra. And okay, in the language of vertex models, so this update, as I have already said, this update can be thought of as a vertex in like colored 6-vertex model. like the simple update. And other generators of Hecke algebra can be thought of like some more complicated vertices. So but like this will require certain work. So what but like the question will be like, what happens if instead of a generator of this form, I consider some more complicated elements in Hecke algebra? Maybe let me go in slightly different order. So maybe because you probably have seen stochastic 6-vertex model. So let me probably just like say that like what corresponds to stochastic 6-vertex model. So in general, so I have a colored case. So this is actually more like 4 vertices rather than 6. If like all types are different, but if some types will coincide, then this will produce 2 more vertices. So stochastic 6-vertex model is basically like this is a discrete time ASEP. So instead of Poisson processes, like one considers just like certain deterministic elements in Hecke algebra which are multiplied to each other. So a bit more in detail. So if I don't care about spectral parameters too much, then I just consider an element in Hecke algebra of this form. So x times like nearest neighbor transposition plus 1 minus x, which corresponds to identity permutation. And then a picture like this from stochastic 6-vertex model, stochastic colored 6-vertex model. So it can be obtained. So for every vertex, we have an element of this form. So with some probability, like one can read this in the following way. Yeah. So with some probability, a larger color goes through, and with some probability, other probability, it turns. Yeah. And then these probabilities, they depend on x, which is actually not a very important parameter. Then they depend on main parameter q, which was present in definition of Hecke algebra and this multiplication. These 2 parameters, x and q, are parameters of stochastic 6-vertex model. And then somehow the configuration of stochastic colored 6-vertex models after like certain number of vertices is just like one element in Hecke algebra. So if I have 5 vertices, this is the product of these 5 elements. And if it grows, then I need to just like consider products of more elements. But like so somehow there is like no probability at this point. But then when I have this element of Hecke algebra, if I want to produce a permutation which corresponds to this right upright exit colors, then I need to do this procedure which was written here. Yeah. So for every even like deterministic element of Hecke algebra produces a random permutation via this rule. Yeah. So it's decomposed into bases. And like the coefficients of these decompositions are probabilities. So stochastic 6-vertex model is so just like corresponds to certain element in Hecke algebra, and then it produces randomness in this way. So so like the way as I wrote here, so I didn't care about spectral parameters. So if I if one wants to have like spectral parameters, then one needs to take this x's of a certain form, so that they satisfy Yang-Baxter equation, and one can one calls this these elements y like Yang-Baxter basis sometimes in Hecke algebra. So like a certain collection of elements which have these spectral parameters in them and which satisfy Yang-Baxter equation. So this is somehow, I would say, this is very similar to like these continuous time processes which I considered before. Like here, like one has discrete time, which is actually a bit more complicated. So it's technically a bit more complicated, but like all phenomena are very similar. Okay, so this was some connection with lattice models, but like my point was that this update is just like one vertex, and then you can organize these updates in many ways. So like what one considers in probability, usually one has like these updates coming independently and like in continuous time and in certain positions of the lattice, but one can organize them in square lattice. One can also organize them in like arbitrary like collections of lines on like R2 and whatever. And also like another important point here yeah, probably like, yeah, connected with what is called solvability, right? So it's that one can take these elements, as I said, from this Young-Baxter basis of Hecke algebra, or like sometimes it's called factorization of Hecke algebra. But in principle, there are also like elements, yeah. So it's not required. So there are some random walks in Hecke algebra from elements which do not correspond to base, like to this like Young-Baxter basis, and they, for example, they will still have this like class position symmetry, this symmetry which comes from involution in Hecke algebra. So one will not have this Young-Baxter equation behind these models, but one will still have a certain Hecke algebra structure behind these models. And this is somehow one level of why I would also say that this is like somewhat integrable, because it also comes from Hecke algebra. But definitely somehow like models which comes like also like which one has a really like Young-Baxter equation, so with generators satisfying Young-Baxter equation, so it seems, at least like heuristically, it seems that they have more integrability, and one can analyze like its stochastic behavior in a much more precise way. But there is a certain somehow, yeah, dichotomy, yeah. So there is a certain choice to be made at this level. So there is a certain like random walks in Hecke algebra is actually much larger class of processes than the processes which are random walks in Hecke algebra, and also which generators satisfy Young-Baxter equation. And now let me try to, in the remaining time, let me try to explain another specific example of particle system, or another specific example of vertex weight, if you wish, which correspond to another choice of generators. So let me define for this. I will need a notion of Mellow's measure on a symmetric group. So this is a probability measure on permutations, which is defined in the following way. So L of W is again, it's the number of inversion and permutation, and then probability weight of a certain permutation W is proportional to Q to the number of not inversions, but like all pairs of numbers of permutation which are in the right order. So n times n minus 1 over 2 minus number of inversions, and then some normalization constant, which is like Q, some Q number. So it's like explicit simple product, but I don't need it. So for Q equals 0, which is perfectly allowed, this measure just concentrated on the word n and minus 1 and minus 2 up to 1. So on the longest word. And for general Q, so it's still somehow exponentially penalize the deviation from this longest word. So it's not very far somehow from this longest word. And so if I have multispecies ASEP on a finite interval of length n, which has one particle of type 1, one particle of type 2, and up to and one particle of type n, so basically this process on permutations, then it will converge exactly to this Mellow's measure. So it can be checked that like this Q asymmetry leads to this stationary measure. So this measure goes back to Mellow's. And also there are like some interesting actually recent work, like quite a lot of them. So in particular, the ones that are related to what I will tell is like the work what happens with these measures, and when n goes to infinity, these works of Canadian and Koleshansky. So like I will need this measure in order to define a certain particularly, I would say, nice element in Hecke algebra, which produces certain particle process, which is fairly easy to describe. So let me try to say what is written here. So I defined certain specific element in Hecke algebra, and it will correspond to certain interval. So I'm thinking, yeah, so I have Hecke algebra elements from 1 to n, and then I pick certain interval inside this like large interval from 1 to n. I pick an interval from A to B, and then I somehow inside this interval I consider basically Mellow's measure on permutations inside this interval, but somehow Mellow's measure and somehow mapped to Hecke algebra. Yeah, so for random permutation, I have certain map which maps this to one element in Hecke algebra. So that's what I'm doing here. So inside this interval, for permutations which only permutes these elements, I for every like TW from such a permutation, I pick a coefficient corresponding to Mellow's measure. And then maybe it's much easier to say like this is the unique element, which is when multiplied to arbitrary t sub w. So if w is from, again, these permutations of only inside interval ab, so this is the unique element, which is somehow, yeah, Haar measure or like one-dimensional representations, whatever. Yeah. So if I multiply it arbitrary tw to this element from left to the right, I will still get this element. So I think, again, so there might be many names. Yeah, I'm somehow motivated by this like connection to probability. I will say that this is Mellow's element for the interval from A to B. So how this element will produce me certain particle systems. So let me start like this slide from bottom to top. So I want to produce the following system, which corresponds to, so first q equals 0. So let me put q equals 0 for simplicity. So I want to produce a system which is called m-exclusion TAZRP. So this TAZRP is very similar to what we had before, to this ASEP. But in ASEP or in TAZRP, we had a rule that inside every position we have one particle or 0 particles. And then if like the second particle tries to jump, then this jump is blocked. And m-exclusion TAZRP is just the same process, but instead of condition that we have no more than one particle at one position, we have instead we have a condition that we have no more than m particles inside any one position. So for example, if I have m equals 4, then, and I have configuration somehow like this, then like from every position one can like the particle, so from here particle can jump to here, from here particle can jump to here, from here particle can jump to here. But if this particle would try to jump to the right, then it will be blocked, because this position has 4 particles and no more are allowed. So this is somehow a system, again, which is known, and I will try to explain how it's related to random walk and Hecke algebra. So I'm presenting a certain specific set of generators. Okay, so they are written here. It's a bit long, probably don't pay too much attention. I'll try to explain the idea, like what is the idea, how to produce this system using generators from Hecke algebra. And the idea is the following. So one needs to think about every position. So like, let's try to move them somehow horizontally. And for every position, we will have 4 positions in our previous setting when we have integers, integer lattice z. And then like if we have like 2 particles, we will always think about like these boxes of 4 elements. Inside them, we will always have the particles sorted. So all particles will be moved to the right, and all holes will be to the left. So that's what will happen in q equals 0 case. And then if we have like somehow such setting that inside every box of 4 elements, particles are all moved to the right and holes are to the left, then by multiplying elements of Hecke algebra, we can do the following. Like the update of this form happens in the following way. So first we do update between rightmost position here and leftmost position here, which actually in this generator corresponds to this nearest neighbor transposition element t. And then we do somehow sorting operations. So after this update, particle will move to the right, hole will move to the left, and then this particle needs to be sorted out. So it needs to be moved to the right. And these 2 particles need to be also moved to the right. So there will be a hole just after one update. Then these particles will need to be moved to the right somehow after such an update. And this multiplication by Mellow's element, it is doing exactly this. So for in q equals 0 case, it just sends all permutations to the longest one. And when I project these 2 particles and holes, it will just mean that all particles will be on the right inside the box and all holes will be to the left. So the point here is that there is somehow non-trivial known probabilistic system, and I can model this by multiplication in Hecke algebra. And if I will run this exactly the same generators, not for q equals 0, but for non-trivial q, I will get also like a known system which is called like ASEP QM. And also like I'm doing this only for particles and holes when I split it like so. But in principle in Hecke algebra, yeah, I have like multi-species process. So in principle, this defines multi-species ASEP QM, which like has like somewhat complicated rules, but they are completely determined by this generator. And there is a certain story. So like for single species, this ASEP QM was introduced in this paper, Carinci, Giardina, Redix, Sasamoto, and like multi-species version was introduced by Kuan. And then this system degenerates into several other known systems. So for example, for m equals infinity to it converges, it somehow it becomes the q-TAZRP, which is like due to Sasamoto Vadati. And also like this operation when like which is sorted inside the box, this is strongly in relation to the notion of fusion, which is due to Kulish, Reshetitkin-Sklein in the 80s, and also like in probabilistic setting, it was also recently discussed in Korvin Petrov. So like my point here, so this was all, again, so this was just like specific example of certain specific generator, but in principle one can one can have like a fantasy and come up with many generators, and one can produce other known stochastic systems, and also I guess one can define many not known stochastic systems somehow, just like by playing with these generators in Hecke algebra, and all these processes will have similar features, both in terms of asymptotic analysis, but also like pre-asymptotic algebraic structure, because they all will come from this multiplication in Hecke algebra. And again, so this multiplication in Hecke algebra is also like, one can think about these update rules, as a weight of a vertex rather than, like I'm saying this on language of particle systems, but one can also say this on the language of weight of a vertex. This is again equivalent languages. So I guess my time is so my time is over. So thank you very much for your attention. I hope this was not too off topic for this seminar. Yeah, thanks.
Thank you so much. Okay, I stopped recording. I don't repeat my mistakes.